All right, let's look at chapter 4. And chapter 4 is going to be taking our chemicals that we talked about in chapter 3 and putting them together to actually make things. And to do this, we're going to have to start out by balancing some equations. So, an equation in chemistry is our recipe for what is going on. So, a chemical reaction is represented by a chemical equation. And a chemical equation is just going to use symbols rather than the words to describe what's going on. So, for example, we could say that hydrogen reacts with oxygen to make water. All right, and if we did that, we could put some words in there, but we want the shorthand on this one. And when we do this, we're going to do an equation. So our symbol, instead of being the words hydrogen, or even the symbol for the molecule, is going to be H2. Our oxygen we're going to symbolize as O2. Please remember back from chapter 3 that you have to memorize the diatomic elements. And our product here is water. And what we have is some things. On the left side, we have reactants. That's our starting material. On the right side, we have products. That is what we're going to end up with. In the middle, we're going to have an arrow, and the arrow frequently means here we have to form. It can be to make or produce or yield, but whatever it is, you're going to start out with something. Frequently, it has a with or and make some products. So we have a reactant side and we have a product side. Now, when we put these together, we have to make sure that no miracles occur, meaning that however many atoms we start out with, we have to end up with. We also include some things in here. We make sure that when we write our formulas, we are representing the actual formula of the stuff that occurs, and we are going to vary the amount in order to have mass conserved from our reaction, from our products or reactions to our products. We change the ratios by changing the coefficients, and these are called our stoichiometric coefficients. Our stoichiometric coefficients are simply our ratios. They don't actually have to be whole numbers, but mostly we tend to work in whole numbers. So we have our stoichiometric coefficients, and they are the ratios of the reactants or the products in order to have mass conserved. So if we take a look at methane, and we're going to do this atom by atom, our methane has this black atom in here, and that's the carbon. And we have one carbon on this side, so it means we have to have one carbon on this side. But they don't come in packages of just carbon. The reactant comes in a package of carbon attached to 4 hydrogens, and that is our methane. So we have to take into account those 4 hydrogens on the product side. And on the product side, those hydrogens are stuck onto water. And if we count them, we have 4 hydrogens on the reactant side. And over here, because we have 2 waters, we have 2 times the 2 hydrogens for a total of 4 hydrogens on this side as well. Now, on the product side, if we look at our oxygens being these red ones, we have 2 oxygens here on the carbon dioxide, and over here we have 1 oxygen on each water and 2 waters, so we're going to have a total of 2 oxygens on this side. If we add these up, this is a total of 4 oxygens. Over on the reactant side, because oxygen exists as a diatomic, they come in packages of 2, and if I need a total of 4 oxygen, I have to have 2 packages of 2. And our balance reaction is methane plus 2 oxygens makes 1 carbon dioxide and 2 waters. Now, we do put a lot more information frequently in there. So our reactants or our reagents are always on the left side. Our products are always on the right side. We are going to go in between the reactants and the products with an arrow. Arrow implies that it goes pretty much 100% to products. When we get to Chem 112, we're actually going to have 2 arrows, telling us that the reaction goes in both directions. We are going to include the state. So if it's a solid, we're going to put S in lowercase in parentheses. If it's a liquid, we're going to put an L. If it's gas, we're going to put a G. And if it is dissolved in water, we are going to put AQ for aqueous. We are going to vary the stoichiometric coefficients, that is the number in front of the reactants and the products, in order to have conservation of atoms and therefore conservation of mass. So in order to do this, we have some rules. One, we have to start out with the correct formulas. We can't change flour into sugar. Sugar is sugar and flour is flour. It's the same thing with chemistry. If we have C2H6 and we need more than one of them, we can't change. So let's say, for example, that we need two of these. We can't change this and make this C4 H12. That is not the same stuff. We have to leave the amount in front with the correct molecular formula in here. And that is the same for both the reactants and the products. If we need more than one of this chemical formula, we change the stoichiometric coefficient in the front. So what would that look like? So first of all, when we take a look and we balance our chemical equations, we're going to make sure that we have the same number of each element on both sides. We're going to start with the most complex, which in this case is C2H6, and we're going to end with oxygen. And we're going to end with oxygen because oxygen appears in 3 of these compounds. Therefore, if we change it once, we can change it anywhere. So we're going to take and start with something that if we change it, will only change one other thing, or maximum of 2 in the case of the water. So here we go. We have 2 carbons. If we have 2 carbons on this side, we have to have 2 carbons. Our carbons, though, come in a package, and they come in a package of carbon dioxide. So if I have 2 carbons, I have to have 2 carbon dioxide. That gives us the 2 carbons. And so we're starting out here as C2H6, and we're going to make ourselves 2 carbon dioxides. And if we like, we can stop, indicate that our element is balanced, and then go on to the next one. The next element here we have to balance is hydrogen. We know hydrogen, here we have 6, and in the reactants, or the product side, we have H2O. So we look at H2O and realize that for every H2O, we have 2 hydrogens. But we know from this side that we need 6 hydrogens. Well, if we take our H2O and we take 6 and we divide it by 2 because we need 6 and they come in packages of 2, we are going to have 3 H2Os, giving us 6 hydrogens and 6 hydrogens. So at this point, our carbons are balanced and our hydrogens are balanced, which leaves us with the oxygens. Now, oxygen comes in a package of O2. On the product side, we're going to add these up. We have 2 times 2 for a total of 4 oxygen. We have 3 times 1 for a total of 3 oxygen. And if we add these up, you're going to get 7 oxygens. Now note, if we like, we can simply go 7 divided by 2, because it comes in a package of 2 here, and have 7 halves. Now most of us do not particularly like having fractions in this, and we take and fix that by multiplying the entire equation through by 2. So what would this look like? So if we have our C2H6 plus 7 halves oxygen goes into 2 carbon dioxides and 3 waters. We're going to remove the fraction by multiplying through by 2. And we do this, we're now going to get 2 of the C2H6s, 7 O2s, 4 CO2s, and 6 H2Os. And we can verify that we have the same or the correct number of atoms and we can do reactants, and we can do products, and we can do carbon, hydrogen, and oxygen. So for carbon, on the reactant side, we have 2 times 2 carbons for a total of 4. On the product side, we have 4 times 1 for a total of 4. On the reactant side, for the hydrogens, we have 2 times 6 for the hydrogen, and that gives us 12. Here we have 6 times 2 hydrogens for a total of 12. And now all we have left is oxygens. Oxygens here are 7 times 2 for a total of 14 oxygens. And here we've got them in 2 places. We have 4 times 2 plus 6 times 1. And if we look at this, we're going to add 8 to 6, which is 14. And we have 14 oxygens, and this is balanced. And we have to do that for every equation. We have to make sure that every atom we start with is accounted for. So let's do a few. And let's start with CH4 plus H2O goes into CO2 plus H2. So if we balance these, we take a look, we've got one carbon, and we have one carbon, and our carbons are balanced. Now, we take a look at this, we need to probably go to oxygen next. Oxygen here, we have two oxygens here, which means we need two oxygens here, and we're going to put that there. If we put two oxygens here, we now have a total of two oxygens and one carbon, but our hydrogens are messed up. Our hydrogens are messed up because we have 4 on this side, plus 4 is a total on this side of 4 times 1 plus 2 times 2, which is 8 hydrogens. And over here we only have 2. Well, 8 divided by 2 is going to give us 4, so we're going to have 4 H2s. And our balanced reaction is CH4 plus 2 H2Os goes into CO2 plus 4 H2. And we verify the elements are balanced. So next one is a nice acid-base reaction. And we're going to take sulfuric acid and we're going to react it with sodium hydroxide to make sodium sulfate plus H2O. When we do this, one of the things that you can do that make your life a little easier is look for common anions. If we notice here, that's a sulfate and that's a sulfate, and we can simply balance our sulfates. We do that, we're removing a lot of the elements from this issue in terms of balancing our equations, and we could do the rest of it now. If we take a look at sodiums, we have 2 here and 1 here. We're going to put a 2 on our sodium, and our sodiums and our sulfates are balanced. This is going to leave us now with H's and OHs. Let you know that water, and a really good and easy way to think of water, is to realize that it is a combination of an H plus attached to an OH minus. OH minus from sodium hydroxide and the H plus from the strong acid. Because I'm going to have 2 H pluses here, and it's going to react with 2 OH minuses here, or note, 2 H's, 2 OHs, I'm going to inherently have to have 2 H2Os. And our balanced equation is simply that. Last, NH3 plus O2 goes into NO plus H2O. So one of the tricks that we can do, and by the way, nothing here is particularly complicated, so you don't really know where to start. So what you can do is start and consider odd and even. Note here with the ammonia that it's an odd number of hydrogens, and over here we have an even number of hydrogens. So I'm going to start by cross-multiplying and get rid of the odd and even problem. So if I do that and I put a 3 in front of the water and a 2 in front of the ammonia, I now have 6 hydrogens, and that's balanced. If I look at my nitrogens now, I have 2 nitrogens and I've got 1 here, so I'm going to put a 2 here. This is going to balance out my nitrogens. This now leaves us with our oxygens. And when we look at our oxygens, we have the odd and even problem one more time, because here I have 2 oxygens and here I have 3 oxygens on the water for a total of 5 oxygens. Because this number is odd and this one is even, I'm going to multiply this entire thing through by 2 one more time. And when I do that, I'm going to get 4 ammonias. I'm going to leave the oxygen for just a moment. It's going to react and I'm going to make 4 NOs, continuing multiplying through by 2, and I'm going to get 6 waters. So now, with that in mind, I can balance out the oxygens. My oxygens on the product side are 4 from the NO, so 4 times 1, plus 6 times 1 for the oxygen from the water, giving us a total of 10. And if I take 10 up here, divided by 2, I'm going to get 5 oxygens. So getting rid of the odd and even can really help in balancing some of the more complicated ones.